Hey, AP Chemsters, this is Mrs. Vandeloy bringing you the 9.10 edition of Blank Wall. This is really exciting stuff. This is the last video for the year, so let's celebrate. Woohoo! All right, so anyway, this is about bond energies and bond length. Bond energy is the energy required to break 1 mole of the bond in the gas phase. These are always endothermic. Why is that? Because you require energy to break the bond. Kind of like a karate board. You go, ah, all right, and when it happens, you break the board. It requires energy to break the board. We're going to do the same thing, go, ah, to these bonds, and we're going to break the bonds. I want to show you something. Why don't you go back to page 5 in your notes? Do you remember this chart here? This is when we're doing the lattice energy. And right here, this step right here, we want to go from a chlorine molecule to a chlorine atom. And what did we need to calculate? We used the bond energy for that. All right, see over here, this is the bond energy to take the molecule of chlorine to an atom of chlorine. We broke that bond in half, so we end up with an atom of chlorine. Look at the next one for fluorine. Go to page 6. Right, go to page 6. There you go. So again, when we have a molecule of fluorine going to a fluorine atom, you took the bond energy. And we did the same thing down here again, bond energy of the fluorine. Okay, so how much energy does it require to break the bond? All right, let's go back to our current page, all right? All right, so these are always endothermic. Why? Because you need energy to break bonds. So do you remember these graphs here? We used them before, and we always start off with the upward trend, right? Why? Because it requires energy to break the bonds, all right? So here's our chlorine gas. Oh, I'm sorry, why? It takes energy to break the bonds. There we go. So here's our chlorine gas going to chlorine atom. It requires 243. Here is the HCl. Requires 434. So why does it require more? Well, HCl is a stronger bond than the chlorine Cl2 is a weaker bond. That's the only thing we can really talk about at this point. What about, well, holy cow, look at nitrogen gas. All right, it's 946 kilojoules. So why do you think it's so high? Well, my recommendation is go ahead and draw the Lewis structure for nitrogen. Go ahead and do that right now. Pause it. All right, welcome back. What did you end up with? Well, what do you notice? You end up with a triple bond. So a triple bond is going to be stronger than a double bond, which is stronger than a single bond. So if you look down here and see if I'm not right, look at this. Here's a triple bond, stronger than a double bond, stronger than a single bond. A triple bond, stronger than a double bond, stronger than a single bond, all right? Because the S overlap, all right, is, the S electrons would give you a sigma bond, and then you end up with 1 pi or 2 pi additional bonds that you have to break, okay? A sigma is going to be stronger than each pi bond, but the pi bond still requires something to break them. So we have the observation going down the group. Look at HF, HCl, HBr, HI. What's going on here? Why would HF, look at it, have the greatest bond energy than all of these going down the group? Why do you think that is? Go back in chapter 8, and what did we learn about going down the group, all right? The atoms get bigger. All right, so as they get bigger, there's less attraction, be easier to break. So fluorine has the smallest radius closest to the hydrogen, therefore is more attraction and harder to break. Okay, so again, it has to do with the atomic sizes and those attractions, and that really depends on how hard it is to break. Okay. What about going across a period? You have HC, HN, HO, HF. What's the general trend here? Well, the general trend is as you go to the right, the bond energy increases. Again, why? The radius goes down. H is closer to the nucleus. You get more attraction. Again, harder to break. All right, so let's go on to the next page then. Okay, so how do we use this bond energy? This is yet another way to determine the enthalpy of a reaction. We found we can find enthalpy of a reaction using many different ways. Go back to chapter 6 again, and you can use it from the Q, you can use it from the heats of formation, you can use Hess's law. But this is the last way we're going to learn how we can also solve for the delta H, okay? So it's a summation of the enthalpy of the bonds broken, which will always be positive. Yeah, takes energy, right? Plus the summation of the enthalpies of the bonds formed. That's your negative. This is like when things come together and energy is released, okay, when bonds are formed. I prefer to write it like this, all right? This is a negative number, all right? You can also put the negative out in front. You can do it either way, all right? This is probably how I will spend most of my time doing it, although I do have an example using this way, okay? So again, we're back to this again, and here is our change in enthalpy versus time. And notice how we have the bonds being broken. This is a positive enthalpy, and this is our bonds being formed. This is our negative, all right? And so what we have here is the difference here is our delta H, okay? So hopefully that makes sense as to what's going on. Just keep in mind, however you want to use this equation or this equation, that the bonds being broken are going to be positive, the bonds being formed are going to be negative, okay? So for example, how do I actually do this? What about methane undergoing a substitution reaction with chlorine to get chloromethane plus HCl? So what's happening here? We are actually breaking one bond, all right? One H comes off, the chlorine bond breaks, one chlorine joins, and the hydrogen joins, all right? So this is really what's going on. And in a sense, I drew out at least the most pertinent parts of the Lewis dot diagram, the structural diagrams, okay? Why is that an important idea? Because, all right, it's good to see what's breaking and what's forming. So this H falls off, this chlorine breaks, the chlorine is formed, and the HCl bond is formed, all right? So bonds broken, bonds formed. So here we add the summation of the bonds being broken, added to the summation of the bonds being formed. Notice that the negatives are here to get negative 113 kilojoules of energy. So here's my bonds breaking, here's my bonds forming, here's the difference, okay? So it says the reaction is exothermic. Oops, sorry. Oops. Sorry about that. That was kind of crazy here. All right, so a reaction is exothermic when weak bonds break and strong bonds formed, and it's endothermic when strong bonds break and weak bonds formed, okay? So it says use the bond energies to calculate this reaction. Well, what was my first suggestion? Draw the structural diagrams. So will you do that for this reaction? Actually draw out using your Lewis structures, just like what we did earlier in chapter 9. So pause this and draw them. All right, well, this is what I came up with. And so if I'm going to use this equation, here we go. What bonds, I'll just put up here, what bonds are being broken? It looks like all 4 of the hydrogens are coming off and all of these are coming off. So what does that mean? So I have 4, oops, wrong one. Try it again. All right, so I have 4 CH bonds. All right, all 4 of them broke. And notice how I wrote this. In one water molecule, I have 2 HO bonds, but I have 2 water molecules, okay? Minus, and I have 4 HH bonds, and I have 2 CO bonds. If you recall, if you go back to the prior page, let's do that real quick. If you look here, you'll do see that a C double bond O is 736, but there's a little asterisk here. What does that mean? It's 799 if you have carbon dioxide. That's why drawing a structural formula is very important. So how do you know if you have a single bond O, C double bond O, C triple bond O? Draw the Lewis structure to know what kind of bonds you have, okay? Let's go back. So you'll see I got the 414. I had 2 times 2 times 2 times 2 is 4, so I got 464 for the HO. I have a HH is 436, and then again I use the 799 because it is carbon dioxide. So when I do that, I get these values here. So I get positive 170. So when I draw this diagram again, here we go. Notice that I am breaking bonds, and that was 3,512 kilojoules. I formed new bonds, which was 3342. So the difference between the two is my delta H reaction, which is positive 170 kilojoules. So that's what this is all talking about. Let's go ahead and do the next problem. All right, so it says write the balance equation for the combustion of gaseous methanol and use the bond energies to calculate the enthalpy of combustion. So take a second out and combust methanol, write down your products. All right, so take a few minutes out, write the balance equation, come back. All right, this is what I came up with. So what's my next suggestion? As always, I would draw the structures out. So take now a few more minutes, pause this, and do the structural formulas like I did the last time. All right, welcome back. This is what I came up with. All right, so hopefully this makes sense. Why is that important? Because this is a C single bond O. This is a double bond O. As you know, this is going to be double bond and water is single bond. I hope you got that. So then let's see here. Here's my equation. And now I'm going to look at the bonds being broken. I just kind of like broke them all. Now, if you really want to, you can say, well, I didn't have to break all of them because here's an OH and here's, I just broke all of them and then rejoined all of them, and it may save you a little bit of heartache there. So I have 3 of the CH bonds times 2. I have 1 CO bond, but I have to multiply by 2. I have 1 OH bond, but I have to multiply by 2. I have 3 O double bond O's here, okay, minus I have 2 of these C double bond O's from carbon dioxide, and then I have 2 OH bonds, but then I have to multiply that by 4. So then I just find all my numbers and plug them all in, and then I do the math, and it's exothermic. So then this is what my diagram would look like. So I break 5,626 kilojoules of energy. I form 6,908. I have a difference of 1,282, and that's my delta H in my reaction. So what I'd like you to do is do this one totally on your own. You can do it. And when you're done, come back. All right, welcome back. Hopefully you got this. Here is my drawing first, and then here is all my work. I have 1 triple bond, I have 3 H single bonds, minus I formed 3 of the NH bonds, but I have 2 molecules worth of that, and up with negative 80, and I'm all set, and then here's my diagram. All right, oops. We have, let me scroll this up again. Bond length, so is the average length of bond between 2 particular atoms. Depends on the type of atom and the type of bond. The weaker the bond, the longer the bond length. The stronger the bond, the shorter. All right, so if the stronger bond, they're going to like each other. They're going to get a little bit close together, aren't they? So notice again, I'm looking at a single bond, triple bond, double bond. While the single bond is the longest of the carbon and the triple bond is the shortest. So looking at the work here, it should make sense. All right, well, let's keep going. Okay, so why do we care about bond length? Well, this really does help about the idea of resonance. Resonance, if you recall, I know it's been a while, is you can draw 2 or more, correct structures given the same thing. Usually it's when you have 1 double bond and 1 single bond. So here I have the ozone. Notice how this bond is a double and this is a single and this is a lone pair. So this is my resonance structure. All right, and notice I took the average between the 2 of them. I took 1/2 of the single bond plus the double bond, and it's about 133. So if you're actually to measure the bond angle, or excuse me, the bond length of ozone, it is not a single bond, it's a double bond, is smack dab in between. But if you look at the next one, and you're looking at the resonance of nitrate, there are actually 3 resonance structures, all right? So given let's look at the top oxygen each time. I have 1 time it's a double bond and twice it's a single bond. So I took the average, if you will, of a single plus a double, and I got 131. So what is it closer to? It's closer to the single bond because it's like 2/3 of the time, if you will, is in the double bond, or excuse me, is in the single bond location. All right, so it is closer to the single bond rather than the double bond. And you know what, folks? We are done. This is the end of chapter 9, and we are done with the year. So can I hear a little woohoo? All right, yippee! All right, excellent. I heard that. And you know what, folks? It's been a real pleasure this year. So I hope you feel the same. So don't wait to be great. Bye-bye.